A very good morning to my respected audience. I would like to acknowledge Mr. Chairman, Dr. Maslan, my dear supervisor, Dr. Aida, and panel of respected examiners, which are Associate Professor Dr. Roshari and Madam Nohafiza. I wish you the best of health in these challenging times of MCO and COVID-19. May God keep us safe and sound, and may He have mercy on our country and our life. I thank God that we can still come together to my proposal defense in an online session. My topic is hybrid Tabu Search for multidimensional knapsack problems. In this first section, I will give a short overview of some concepts so that you have a structure and background to understand the problem statement and purpose of the study. The knapsack problem model is a general resource allocation model whereby a single resource is assigned to a number of alternatives with the objective of maximizing the total profit. The general form of KP is found in the following three equations. In the first equation, which is the profit equation, it is the sum of Pj times Xj, P being the profit or benefit of alternative J, and X being the decision variable of whether to include alternative J or not. In the second equation, which is the constraint equation, the profit equation is subject to the sum of Wj times Xj, which must be less or equal to C, W being the weight of alternative J, and C being the total capacity of a single resource. In this model, Xj is part of the set of 0 and 1, meaning that this solution must be a binary solution, and J equal to 1, 2, n variables. For a multidimensional knapsack problem, it is one of knapsack variants. The KP considers only a single resource, while the MKP considers multiple resources. The resource constraint for MKP is expressed in equation 4 below. For the constraint equation for MKP, it is the summation of Wij times Xj, which must be less or equal than Ci. So because of multiple resources in C, Wij will also be multiple. The Tabu Search meta-heuristic uses memory concept in order to optimize its search processes. Tabu meaning that the solution cannot be revisited after it has already been chosen in the previous steps. Here I would like to bring you through a simple Tabu algorithm model. So it starts with an initial solution, and then it generates candidates, and then the candidate moves are checked against the Tabu list to decide whether it is a Tabu move or not. After that, a list of candidates are generated and put into a list. From that list, the best solution is selected. The best moves are recorded. At the same time, it is also recorded in the Tabu move. After that, the meta-heuristic continues until a stopping criterion is reached, for example, the number of iterations. So the important step in this algorithm is that all the best moves or solutions selected are recorded in a Tabu list, whereby in future iterations, all the moves will be checked against this list to make sure that the previous solutions are not revisited again. Hybrid Tabu has been used previously in solving NKP. Here I'd like to mention two cases, two studies. One was by Chang in 2010, whereby a study was done on protein structure prediction, which used Tabu Search to overcome the shortcomings in GA by applying a hybrid configuration. Another study done by Ketari in 2013 was a hybrid algorithm with features inspired from Tabu Search by incorporating essential particle swarm optimization queen algorithm. This technique has successfully resolved large-scale MKP01 instances. The strawberry plant algorithm was first introduced by Salhi and Fraja in their 2011 study. Conceptually, plants such as strawberry grow both runners and roots for propagation and exploitation for resources such as water and minerals. The behavior of a strawberry plant can be modeled through the following three characteristics, which was explained by Merrick Bayat in 2014 study. First is that each strawberry plant is propagated by randomly propagating runners, which represents a global resource search. Secondly, each strawberry plant grows roots and root hairs randomly, which represents local resource search. The difference between a global and local resource search is that global search is a search which goes at a further distance than a local resource search, which is normally a local search and it might be just a one-step add or move. One-step add, move or drop move. The third characteristic is strawberry plants that have access to rich resources grow faster and produce more runners and roots, while runners and roots heading towards poor resources are more likely to die. This is the concept of survival of fittest, and every iteration only the best solutions are selected for the next propagation process of runners and roots. Here I'd like to give you a brief explanation of a diagram of strawberry algorithm, which was sourced from the study by Merrick Bayat 2014. So you see here in this diagram there's x1 and x2, which are the original mother plants. So in the first generation, each mother plant will produce a root and a runner. Here it also produce a root and a runner. However, in the next generation, in the next cycle, this root solution and this root solution was not chosen to propagate in the next generation because these two solutions were inferior solution. So only the runner root here generates the next solution here, a runner and a root, and the solution from x2 runner also generates a runner and a root. In the third cycle, you can observe that the root and runner of this mother plant was not selected because these two solutions are inferior than the root and the runner of x2 plant. So these two plants is selected in the next cycle to the next runner and root generation. Here is the problem statement. The designing an effective technique for the MKP form has many practical benefits as it can be transposed into other forms. Second is, hybrid Tabu Search and SVA is a novelty and should be explored in its effectiveness to solve NKP. And optimal starting parameters are essential to ensure good quality output, and data mining methods with factorial method testings can be used. Fourth, this study aims to generate a good quality solution of NKP by applying a good meta heuristic technique, a greedy heuristic, and a parameter tuning technique. My research questions are: what are the suitable techniques to construct initial solution? Second, how to improve the initial solution? Third, what are the suitable starting parameters to set the hybrid Tabu Search as a strawberry algorithm? Fourth, how to evaluate the quality of the proposed techniques. My research objectives: firstly, to construct the initial solution using greedy heuristic approach. Second, to improve the initial solution using hybrid TS-SBA. Third, to determine the optimal parameter setting by using factorial, design of experiment, and decision method. And fourth, to evaluate the quality of the proposed techniques by using the MKP benchmark dataset. My scope of study will be to examine a total of 270 MKP benchmark datasets retrieved from OR library that can be accessed in this website. The contribution of the study is this study proposes a novel hybrid TS-SBA to solve NKP and evaluates its performance. The significance of the study is that the proposed algorithm may assist decision makers to resolve other variants of KP with minor modification. This chapter presents a review of the past studies that are directly associated with this present study. The review begins with an overview of techniques that have been applied to solve NKP. Next, the review continues to explain the constructive heuristics that have been used for MKP, for KPs. Past studies that have employed TS for solving knapsack problems are also reviewed. Studies of real-life problems that use SBAs as solution will also be looked into. Finally, this chapter presents the method used to perform parameter tuning for meta-heuristics. A range of exact and heuristic algorithms has been developed to solve NKP. Exact algorithms are based on dynamic programming, branch and bound method, systematic approach, and MKP relaxation techniques, such as Lagrangian, surrogate, and composite relaxations. Some popular meta heuristics have been used by researchers to solve NKP, including variable neighborhood search, evolutionary algorithm, genetic algorithm, artificial algae algorithm, ant colony algorithm, simulated annealing, and Tabu Search. In recent years, a number of hybrid algorithms, particularly used for NKP, have significantly outperformed the individual pure approaches. Studies by Banda, Velasco, and Baronis 2017 and Justrom 2005 has found that greedy algorithms are efficient and has low computation costs. Studies which have solved the single constraint KP using bang-for-buck ratios in constructive heuristics are such as Bellis and Zemel 1980, Nears 1976, and Salkin and De Kluver 1975. The Tabu Search method has been used extensively to solve knapsack problems. Salem, Hanafi, and Tak and Abdallah in 2017 has used a probabilistic taboo to solve a disjunctively constrained knapsack. Yang, Wang, and Chu in their 2013 study has used a hybrid greedy randomized adaptive search procedures and Tabu Search to solve quadratic knapsack problems. Also, Alide, Ramalingam, Wang, and Catley in 2018 has used a critical event Tabu Search (CETS) to solve a multi-dimensional knapsack general integral problem. Strawberry algorithm has many applications. It has been used to design off-grid integrated energy systems for mining operations in a study done by Frege and Amuset 2016. It has also been used to design distributed generator for generation network. It has also been used in enhancing efficiency of warehousing systems, multi-objective beer fermentation optimization, as well as optimizing reservoir operations under a study done by Aswini and Amuda 2017. A successful meta-heuristic application to specific problems requires a good initial parameter setting. According to Dobbs law in 2010, he has asserted that effective initial setting of parameters has a significant impact on the solution performance, such as search space exploitation or explosion rate, and hence the solution quality. The design of experiment DOE has been used to obtain the largest information possible with the least number of experiments, according to Donnelly 1984. A popular DOE method, which is the factorial design, is widely adopted in many meta-heuristic studies, such as Adonso-Dias Laguna in 2006, Falahi Amiri and Yagini in 2014, and the study done by Gunawan, Lau, and Wong in 2013. Several studies have used data mining and machine learning methods for parameter tuning. In the studies in 2004 by Bhattacharya, he has used the F-race method. In Khoury and Ripa-Singh 2017, they have used a genetic algorithm enhanced by machine learning techniques. And in the study done by Dobbs-Law 2010, he has used a four-phase approach using DOE and artificial neural networks. This chapter presents the methodology that will be adopted in this study. We will be looking at DEMA, a framework for meta-heuristic studies, the design of hybrid TS SVA, and the method of parameter tuning. In the final portion, I will share the expected findings and go through the timeline for this study. This study will adopt the research framework adapted from design and implementation methodology for meta-heuristic algorithm, or DEMA, which was introduced by Yagini and Akavan in their 2011 study. The DEMA framework will be illustrated in Figure 3. In this framework, you can see it consists of three phases, which is Phase 1 initiation, Phase 2 design, and Phase 3 construction. Under Phase 1 of initiation, you have 4 steps. The first step is stating the problem. In our case, the problem will be the MKP problem, and we have already given the mathematical formulation in the introduction. Step 1.2 is define the goals. So the goal of our study is to solve a maximization 0-1 binary encoded MKP problem. In 1.3, we do a literature review. 1.4 is a select instances. A total of 270 standard instances of MKP problem will be selected from OR library for this study. These instances are commonly used in meta-heuristic experimentation, and the best outcomes retrieved from this experimentation are commonly published in the literature. Under Phase 2 of design, we have Step 2.1a, which is selecting the heuristic solution strategies. This step is for us to create an initial solution using a greedy heuristic. Before we move into the next step, let's look into detail the steps for a greedy heuristic algorithm for initial solution. The greedy heuristic algorithm for generating the initial solution. In the first step, we compute the utility ratio U for each decision variable of X. Variable U is equal to P over C, where P is profit coefficient and C is the cost coefficient. In the second step, an index of decision variable is created, X, based on the sorted utility ratio U in descending order. Then, solution S is generated by adding iteratively X decision variables in the order of sorted utility ratio U while constraints are not violated. At the first violation of constraints, the solution S is backtracked to previous feasible solution, whereby that solution is used as the initial solution for meta-heuristic. In step 2.1b, we will select the meta-heuristic solution strategy. This is the improvement method which we want to use to improve from the initial solution. In our study, we will use the hybrid Tabu Search algorithm. Next, we will zoom in into this hybrid algorithm and look at its design. This is the flowchart of the hybrid Tabu Search. So the meta-heuristic starts by generating an initial solution using greedy heuristic. And then it goes on to initialize the parameters of the meta-heuristic, which are the length of runner and roots, the number of mother plants, the move taboo list for each taboo plant. And then we go on to duplicate n number of mother plants from the initial solution XO. In our meta-heuristic, we will duplicate 4 mother plants. And then we go on and randomly generate a feasible runner, X runner, and root, X root, for each mother plant X by generating moves D for each mother plant. So we will have 8 candidates from the 4 mother plants, because each mother plant will generate 2 candidates, so we have 8 candidates altogether. And then we go on. Here is a decision node where the algorithm will check whether the add and drop moves of the candidates are part of taboo list. If it is, then these candidates are removed from the candidate list N. And then if we do not have enough 8, once these candidates are removed, the candidate list will be less than 8, and what happens is we will regenerate another candidate so that the total candidates in the list will equal to 8. Next step is we will calculate the fitness and Z of each runner and root, and we select the best half of the new locations as the mother plant for the next generation. So out of 8, we will select the best half and we get 4. And then this algorithm will check whether the termination condition has been satisfied or not. In our case, the stopping criteria would be the number of iterations that we set for this algorithm to run. When we select the best 4 of the candidate list, we will set the moves for this best 4 into the taboo list TD. Okay, And for every iteration which this algorithm runs, TD has to be reduced by 1 at each iteration cycle. So if the termination condition is not satisfied, you just go up and run the algorithm once again. Now let's return to the DEMA flowchart again. Step 2.2, define performance measures. To define a performance measure is to determine measures which we will use to evaluate the performance of our meta-heuristic. In this study, the performance measures are the comparison against the best known solutions found in literature that will use the same 270 test instances retrieved from OR library. In step 2.3, we will design the algorithm. Under phase 3 of construction, 3.1 is to implement the algorithm. In our study, we will implement the algorithm using MATLAB programming language. Next is step 3.2, which consists of tuning the parameters. To do parameter tuning, first we set the range of parameter settings which we want to test and which we will use to run a factorial function. Then we will generate the training data. Let us look at some of the parameters which we will be using. With total levels of 15, we are able to generate 108 combinations or data which we can use as the training data for our decision tree model. Next, we will train the decision tree model with the data and use the train model to make a prediction on the optimal settings for the meta parameters. Let's have a look at an example of a decision tree model. After generating a predicted decision tree model, firstly, we look for the node which gives us the highest reading of the predicted Z value. Next, we will trace the path of the parameters which has given us this highest Z value. So for example, here, we will use parameter values of between 4 and 6 for parameter x6 and values less than 4 or 0 for parameter x7 to achieve the predicted higher Z score. Based on these parameters, we will use these parameters in the test input values for our 270 data sets. Okay, and x7 parameter we will use 4 or missing. Lastly, we use the predicted parameter settings to run the 270 data sets. Step 3.3. The performance of the hybrid Tabu Search algorithm is analyzed after testing the algorithm with 270 datasets for 100 iterations. The results are summarized and presented in tabular form and later compared against the benchmark results. Finally, step 3.4 is to document the results. Comparison of the study outcomes against the best known results found in literature is performed and documented. From all these steps, we hope to achieve 4 objectives. The first objective is to construct the initial solution using greedy heuristic. The second objective to be achieved is to improve the initial solution using the hybrid Tabu Search and strawberry algorithm. Objective 3 is to obtain the optimal initial parameter settings using decision tree. And objective 4 is to evaluate the quality of the proposed techniques using the MCAPI benchmarks. For my expected findings, this study is expected to achieve all the study objectives. The expected findings are given as follows. 1. A greedy heuristic algorithm, and 2. A new hybrid Tabu Search algorithm. This is my proposed timeline. So now we are in early April, where I finished doing my proposal and also completed my coding. In the month of May next month, I will be running the algorithm to compare against the benchmark results. And the next 3 months, I will be preparing for my Viva and completing chapters 4 and 5 for a complete thesis. So we are done. Thank you all for your patience and taking time to review my proposal presentation. Finally, I would just like to wish all of you safety and may God bless you and keep you safe in a challenging day.